So today's lecture will be about test data generators. So on the face of it, this sounds like a very specialized topic, and it also sounds very unrelated to what we looked at last week, which was I/O. In fact, we're going to use this example to understand a bit better about a more general mechanism that is in Haskell. And I/O, that we saw last week, is an instance of that general mechanism. Today, the instance we'll look at is how we make generators for test data. This is quick check test data. Quick check, remember, uses random data generation. And quick check knows how to generate random data for a number of built-in data types, but it doesn't always know how to generate the kind of data that you want for the particular tests you want to do. And in particular, it doesn't know how to generate data for new data types. And this is something we will see in today's lecture. Now, I'm going to start by looking at an example that we looked at the end of the last lecture. So last time we looked at this function called do twice. And if we give an example of it, if we do twice something like, if we print something to the screen, then it will run the instruction twice and return the two results that were obtained from running that instruction. Now, this is not a great example because the results of a print operation are just the unit type, which is not terribly interesting. What happens if we do twice on getLine? So think about that for a second. What do you think it will do? Well, it should run getLine twice and return the pair of results that those two I/O instructions gave. So it's waiting to get a line, and now it's waiting to get another line, and now it can return the results of those two, running those two instructions. Okay. What if I take one of the things that I just did, let's say this one here, and put it inside a list? Is that allowed? Can I take the length of that list, for example? That's a list of what? Yeah, it's an I/O something or other. So there's one thing in that list, and it's an instruction. So there's a list containing instruction. So of course we can do that if we like. What about this? What will this do? Somebody said show list. Anybody? What do you think it might do? Oh, let's see what it does. It says there's no instance of show for this. There's no instance of the show class for this. What that means is it doesn't know how to print an instruction, right, and something of type I/O of something. It doesn't know how to print it. The same applies to, you remember the function abs? Takes a number and gives you its absolute value. The same goes if we we can put abs in a string. That's a list containing a function, and we can ask what the length of that list is. But we can't print out the value of that because we don't know how to print functions. Functions are not something you're supposed to print. Functions are things you're supposed to apply. We're not interested in printing functions. The same goes for things of type I/O. We're not interested in printing the instructions that make up an I/O. How we represent those instructions, there may be many different ways to do that. We're not interested in that. That's not what computation is about. We run instructions, or rather the runtime system will run instructions. We apply functions. That's what we do with functions once we really want to get some action. Okay? So I/O is a first-class thing, like a function is a first-class thing, but that doesn't mean we necessarily can do everything with it, and in particular we can't print it. Now, what is the type of do twice? Well, we used it at a particular type, namely you give it an I/O of something and it returns, the result is an I/O of a pair of those somethings. So if you apply it to something of I/O string, which was the getLine function, then the result of doing an I/O is an I/O of something. We know that because there's a do out there, and it will produce a pair of strings. So it's an I/O pair of strings. What's the general type of that? Well, it turns out that I/O is just one instance of the way we could use a function like this. That is to say, do notation with these operations and this return function are all things that apply not just to I/O, but anything, any M, which is in the class monad. So we've been using the I/O monad, but there are other monads. In other words, these are instructions of many different kinds, depending on what the type of the monad is that you're talking about. If we're talking about I/O, then this will be a way of building something of type I/O from other things of type I/O. Today, we're going to see quick check instructions. Instructions that quick check can use to generate random data. Now, what kind of things can quick check do random testing on? Well, it uses a type class called arbitrary. Quick check can do random testing on anything, any data, any type in the class arbitrary. What's important about arbitrary? There's in the class arbitrary, there is a random value generator. Now, this is a quick check random value generator. This is what quick check uses to generate random values. And the type of that is called a gen of A. Okay, so gen of A is a quick check random value generator. You can think of it as another kind of instruction. Instructions for generating random values. So gen is also in this class monad. So these are instructions that can be built using the same operations that we use to build things of type I/O. Namely, we can use do notation, we can use functions like return, and so on. Okay? So the analogy then is that these are somewhat similar kinds of things in the sense that they are a data type, an abstract data type. We can't look at how the internals of the data type work for representing kinds of instructions. I/O of A, they're instructions to build a value of type A by interacting with the operating system. We can't see what those instructions look like. The only thing we can do is give those instructions to the runtime system, and the runtime system will actually run the instructions for us. So it's the runtime system who actually takes the instructions and actually does something with them. Similarly, Gen A, the type that we're going to be looking at today, will be instructions to create random values of type A. These are not things that are run by the GHC runtime system. They're things run by other functions that are found in the quick check library. Quick check will automatically use generators that we define in order to generate its random values. Okay? All right, let's go back and have a look at some actual examples. So we can ask about gen, and it tells us a bit of information about where it's defined. But in fact, the way that QuickCheck uses this type is to use a class called arbitrary. And the important thing to know about this class arbitrary, apart from the fact there's a whole bunch of instances, things like bools, chars, doubles, ints, integers, lists, and so on, is that the class arbitrary contains a definition of a little arbitrary, which is a generator for an A. So something can become a member of the arbitrary class if there is, most importantly, a function called arbitrary with a small a. Arbitrary is a random generator, but most importantly, it's the one that QuickCheck will automatically use to generate values of a given type. Okay? So we're going to look at how to construct generators. The specific generator that QuickCheck will use when it generates random values is this one. Okay? We're going to see how to build these things and how to then make our own types an instance of the arbitrary class by defining the generator we want for this guy. In other words, the generator that we want QuickCheck to use. Now, there are a number of ways we can explore the values that QuickCheck generates. We saw one example earlier in the course, and that was a function called verbose check, which was just like QuickCheck, except that it shows you the test cases that it generates along the way. Now, the QuickCheck library provides some other functions that we can use to inspect generators. These are functions that we use when we're building, debugging, and just trying to understand the generators that we create. And they're functions called sample and sample prime. And I'll show you what they do. So sample, you give it as an argument a generator, and it will give you a few examples of values that QuickCheck would use for that generator. So what is a generator? Well, this generator called arbitrary is one such, go away, junk mail. Arbitrary is one such generator. It's one that where we have to specify the type. We say, what do we want to generate? We want to use the function arbitrary, which is the predefined generator for a number of types. We have to tell it which type we want to use, otherwise it will use a really boring type. Let's say we want to generate integers. So we use arbitrary at this type, and we sample the generator, and then we see a bunch of sample values that are printed out. Another variant is to use sample prime, and sample prime will just give us a list of those values. That's more helpful here because they'll all fit on one line. So we can sample a generator at a given type, and QuickCheck already knows how to generate things like integers, and it also knows how to generate any pairs of things as long as it knows how to generate the elements, or any lists of things as long as it knows how to generate the elements. So we could do a generator for pairs of int and lists of bool, for example. And QuickCheck will know how to generate those automatically. It will already be in the class arbitrary. And so here we see an example of random values of type int and list of bool as pairs. Okay? Any questions about that so far? So we have some built-in generators already. QuickCheck has a bunch of those. All right, so that's arbitrary. Now, we're going to look at how we write generators. Let me give you an example. We have a function already that can be applied to a generator. That's do twice. Do twice can be applied to any monad, not just IO. It can also be applied to gen. So what do you think it would do if we do twice applied to our arbitrary type generator for ints? What will that do? Well, what is this thing? What is the type of it? It's a generator for pairs of integers. You give it as an argument a generator for a single integer. It will run that, you will use that generator twice to generate two integers and return the pair of those integers, rather ints, short integers. Okay, if we want to look at what this produces, we can't do that. We can't just type that because it doesn't know how to print it. But what we can do is we can sample it. So let me sample that. And then we see now we've taken a generator for a single thing and turned it into a generator for pairs of things using the function do twice. Okay, so what you've seen then is that how we can use the do notation that we saw for I/O in a very similar way with our random value generators. What this will do, this will correspond to the value that is generated by this random generator. There's a question.
What are the values really close to 0 at the beginning and then really far?
Right. Okay, so it's important to remember that quick check is not a statistical library. So it doesn't use particularly meaningful statistical distributions of values. What quick check typically does, as its heuristic for helping you find bugs, is start with small values, and then gradually, the more values it generates, the bigger the values get. So that's the general strategy you'll see in all quick check generations. It'll pretty much always start with small values, and then they will grow. So I think when we saw the examples, the other examples here, the initial things that it tests are always small things, and then they start getting bigger, and they quite quickly get more substantial. And that seems like that turns out to be quite a sensible testing strategy. Yes, a question?
I'm not sure I understand the syntax where you have arbitrary and then gen int. I mean, are you...
Okay, yeah, the syntax here. So this is...
So that's a type signature, isn't it?
It's a type signature. So what you can do inside any expression in a program, you can add a type signature. And what this will do is ensure that this arbitrary here, which has many different types, polymorphic, is used at a specific type. If we leave this out, you may remember when we were doing quick check, when we leave out type information, however we do it, if we leave out type information, the runtime, the GHC, will choose the simplest type. And the simplest type is usually pretty bad for testing. So actually, this is not a feature of quick check. This is a feature of GHC. When it doesn't know what type to use, it chooses the simplest type. And the simplest type is this one. We don't want it to use that type. We want to use a different type, but it can't know what type we want to use, so we have to tell it which instance of this function, this overloaded function, do we actually want to use. And one way of doing that would be to do this.
So arbitrary itself is a function defined in the picture.
So yes, arbitrary, if we have a look at what's the information about arbitrary, it's something in the arbitrary class, it has this type, and it's defined in this submodule. Okay, so we've seen at least evidence from the do twice function that we can construct our own generators using the same notation that we used to construct I/O instructions. So let's look at some example of that. Let's write a generator for even numbers. So a generator for even numbers, this is going to be something, let's say that evens, let's give it a simple type, a generator for int. So how will it work? How do we build something of this type? Well, we know that we can use do notation. And what are we going to do? Well, let's suppose we generate an arbitrary, we use the function arbitrary to generate an arbitrary int. Let's call that arbitrary int that we've generated n. Now what do we want to do? Well, we want to return, we're going to use n to return an even number. How could we take an arbitrary number and turn it into an even number? We can multiply by 2. That's right. So we're going to return n times 2. Okay? Now, we didn't have to specify the type here as we did when we did it on the command line. Why is that? Why didn't we need to do that? Yeah.
Because the do blocks return the type of the function.
Yeah, the do block, and we've given the main thing is we've given the type of the function. Because we've specified the type of the function, Haskell can infer that the type of this arbitrary must be a gen for int. That's why we didn't have to put the type in. Okay. All right, so this generates an arbitrary int using quick check's built-in generator for arbitrary ints. And then we turn that into an arbitrary even by multiplying that by 2. Let's just compile that and test it. Let's sample prime the evens. And then we see a sample of increasingly growing even numbers. Okay? Any questions? All right, now if we wanted to, let's take another example, the natural numbers. So this is also a gen for type int, because we don't have a natural number type. What will we do in this case? Well, we'll do something rather similar. You can see where this is going, right? What do we want to return? If we want to return a natural number, we use the function abs. If we can spell it, we use the function abs. So nats now will construct another random number, another generator for ints, but this time they will always be greater than or equal to 0. So let's just reload that and sample it. And there you see nothing negative in that list. Sample it again, we get some different ones. So on. Any questions about that? Now, what do I usually do when I see myself doing cut and paste? Cut and paste. We usually think about, this is really a place where a higher order function belongs. So what is going on here is that in both cases, we have a function. In this case, it's the times 2 function. In this case, it's the abs function that we're applying to the value that's inside the monad. The monad here is gen. Okay, so we want to apply a function to the thing inside, the int that we could get out of it. Okay. So what we have to do is we have to use a do block to get inside, apply the function, and then return the gen back on the outside. Okay, so this is a very common pattern, and it turns out that there is a function control.monad lift m that applies not just to evens and nats, but any monad. Oh, sorry, spell it right. It's with a small l. Of course, it's a function. I want to ask information about it. I don't want to print it out. So give me the information, give me the type of it, for example. So it's a thing, if you give it a monad containing an A and a function from A's to R's, we'll turn that into a monad containing an R. So for example, we know that getLine that we looked at earlier, the type of that is an IO of string. If we wanted to do something like apply the function take5 to the string that we would get, inside the string from inside the monad, we can't do take5 of getLine because the types don't work. GetLine is not a string, it's an IO of string. So we want to do our get line and apply this function to what we get out as the result. We can write a bit of code like this using the take 5 function instead of the abs function, and that would work. But we can instead use lift m. Now it turns out lift m is not in the prelude, so we'd have to import it. But it turns out that there's another function, a closely related function, that is identical to lift m for things like gen and io, and it is in the prelude. And it's a function called fmap. And it's usually used in infix style, so it's fmap. So fmap will do the same job as lift m without having to import it. So I'm just going to use fmap here. And it's used pretty widely. So now what we'll do, if we do this, well, we're running the getLine instruction just as before. It's still an IO of string, the type of this thing. I can type my stuff in. It will read that, turn it into a string, and apply the take5 function before constructing the contents of that IO. So the IO result will be just the first 5 characters. What that means then is that we could define this thing alternatively as arbitrary fmap, sorry, getting my arguments the wrong way around. I want to apply abs using fmap to arbitrary. Let me sample that. Let me sample that thing there that I just typed, just to show that it does the job. And there it does the job indeed. You notice I didn't need the type here because it knows that abs is a function that takes numbers. Any questions?
Yeah.
Yeah.
Why here it's a low number and not grown as?
Okay, yeah, that's a good point. Let me just look at the type of that thing there. There is a good explanation for that. And it won't be something you would have seen so far. So the type of this thing is a general type. It works for any number. Any number. Why any number? Because abs only works on numbers. But whatever number it is, it has to also be something that has an arbitrary function. Okay? So any number which we can randomly generate using arbitrary, this will be a generator. But still, when we run this thing, we still have to pick a type. And then there has to be a default rule for what type you pick. Now, we can't pick the type, the runtime system can't pick the type unit because unit is not a num. So it has to have an idea of what is the most kind of, what is a representative, the simplest num. And it uses integer instead of int. So integers, ironically, seem to grow more slowly in quick check than ints. So we should be able to fix that. Let me just, or rather observe that. In practice, if we put in a type signature for arbitrary, and I think I'll need the brackets here, so I'll put them in just to be on the safe side. It should be a gen of int. So if we use arbitrary at that type, rather than an arbitrary type, then they'll grow much quicker than if they are at type integer. I'm not quite sure what the philosophy of that is in the design of the library. But integers grow more slowly than ints, even though integers are the things that can grow arbitrarily big and ints aren't.
Probably the performance, so not to overhead the integers.
It might be that, but it might be that bugs in programs that use bounded size ints can only be revealed by choosing big ints, because they involve things like overflow, wrapping. You take a big int and you add to it, you'll wrap round to 0 again. That's a kind of bug where you really shouldn't be using ints if your ints are getting that big. So it would make sense from that point of view for quick check to actually test some big ints, even though ints are not supposed to be big. Okay, Let's look at some more ways of constructing generators. So the quick check library contains a whole bunch of things. So here's the appropriate module of the quick check library, the gen module. This contains a whole bunch of functions of relevance to constructing generators. And we're going to look at some of these today. We've already seen sample, which takes any generator which can be printed on the screen, generates a bunch of them and actually prints them on the screen. So it results in an instruction for printing them on the screen. You see sample prime actually has a different type. It also does I/O, but it actually returns the generators, the values that it's generated. So you could, in principle, even use sample prime in other programs. What I'm going to look at is some of these guys here, ways of building generators from other generators. Okay, let's take some examples. They're pretty easy to get the hang of. The first one, choose, is something which is closely connected to the system random generation suite. It basically says, if you give me any type which can be randomly generated by the system random generation, and you give me a range for that type, I'll create a generator of that type. So basically it's reusing the built-in random generation routine. That would be my guess. Okay, so what things are of this type? Well, only really basic things: numbers, characters, booleans, nothing fancy. So random, system random, things that can be randomly generated are fairly limited. But we can certainly use it for numbers. So if we want to sample, let's do sample prime for choose, and then it takes a range and as a pair, for some reason, something between 0 and 100, then we will always get things between 0 and 100. Okay. Another example, let me look at the type of one of. You give it a list of generators and it will randomly choose one of them and generate a value using that one. Okay? So for example, if you want to sample prime from the list of generators, evens, do we call it evens and nats? Yes. Evens and nats. That will either generate even numbers or nats. That's probably not a very good example. Let's generate odds. How would we generate odds? Odd numbers. Evens minus 1. I like that. So we'd like to do evens minus 1. Can we do that?
Minus 1 to...
Yeah. So we have to use our fmap function. We have to fmap minus 1 over the evens in order to convert the evens into odds. So that will be a way of writing the odds function. If we sample that, we will get, okay, let's not do evens, let's use nats. So we get even numbers. No, that's not going to really be very, so let's, yeah. Evens and, okay, yeah, odds. Let's do negative odds. Shall we do negative odds? Let's take the minus 1. Minus n minus 1, will that work? Possibly. There. What am I doing right here? Didn't sample, yeah, what am I talking about? Yeah, so I'm sampling list of two different functions. This one is going to create negative odd numbers. This one creates arbitrary even numbers. I don't know, what am I doing? List of, with a big O. Oh my God. All right, let's keep this a bit simpler. We're gonna take a list of. What was it we were trying to look at? We were trying to look at one of, not list of. Sorry about that. One of those two things. Let's take another example that maybe is a bit easier to see what the hell's going on. Let's do there. That's a random number generator. It randomly generates the value 42 every time. So we sample that, we see we'll get, roughly half the time we'll get the value 42. And the rest of the time we'll get even numbers. Sometimes we get more 42s, sometimes we get less. Okay. That was a better example than trying to get too fancy. Okay, what's next on the list? We've just seen return. That creates a generator. We've seen one of. Elements is a little bit simpler. Elements just takes a list of things and it gives you the random generator, which will just randomly pick from that list. So we want to sample. If we want to sample, suppose we wanted to sample things, strings, or let's say characters. We sample characters. So we sample arbitrary, not argument, arbitrary at type generator for characters. What will that look like? Well, it'll look pretty ugly. It'll look pretty ugly because it generates, these are all control characters. So that's a typical example of a standard generator that you might not necessarily want to use in certain programs. You might want to use your own one. It would be maybe nicer to generate from the elements of the list from maybe A to Z. And then we see we get alphabetic random strings in this case, because sample creates a list of characters, which is printed as a string. Any questions? Okay, frequency is a way of adjusting the frequency of the generated datas. The type of frequency, it takes a list of pairs of a generator and a weight. And it's basically weighting the chance that you will pick the given generator. So if I take one of my earlier examples, which was this one here, evens and 42, if instead of one of we use frequency, then we can weight the probability. Let's have a small probability, with a relative probability 1 to 10, which means that for every roughly 1/10 of the time we will generate an even number, and the rest of the time we will generate, well, let's say that will probably be 9, that will give us probably 1/10 of the time. 1/10 of the time evens, 9/10 of the time will give us the value 42. Yeah, seems about right. Okay, any questions?
Where is it defined how many elements the sample prime
It's just an arbitrary constant that's thrown in. So remember, sample prime is not a sort of serious programming tool. It's really just a way of debugging the generators that we're going to build. So yeah, it'll be deep down in the library. I don't think it's a configuration parameter. The parameters of quick check itself, however, the number of test cases and so on, they are configurable. There are more general functions that you can use to set those manually. Quick check is basically doing a checking operation using a standard set of default parameters, but you can change all those parameters. We're not going to look into the details of that. You'll have to have a look at the quick check manual. But sample, I don't think, does that. But I think there are other functions in the quick check library where you could rebuild sample, in fact. Okay, time for a break.